Now that we know the general shape of our system response, let's look at how can we analytically sketch this and get a pretty good picture from looking at the transfer function and then the parameters that we get out of it, that natural frequency, damping ratio, the A value, and the B value from our input. We're going to focus in on underdamped systems only in making sketches in this unit, and we're going to continue that into Unit 3. Now, there's certainly usefulness and that comes up with critically damped and overdamped systems, but that's outside the scope of what we're going to look at in this course. So here we have a picture of a very general second order system response for an underdamped system, and we're going to look at some of these key values here: rising time or rise time, the peak time, the max overshoot or just overshoot, and the settling time are initially what we're going to be considering. So calculating the rising time. The rising time we're really not going to use that much, but it does come up in system performance. So the rising time is usually defined as the amount of time it takes to go from 10% to 90% of the steady state value. So it's that TR in the picture below. So to make that calculation, we're going to take 1.8 and divide by the natural frequency. And that's, again, the time it takes to go from 10% to 90%. There are other definitions of rise time that could come up, like 5% to 95%, but this is the one that this book uses. Peak time we're really going to use a lot more. So this is the time it takes from when we start to when we get to that maximum value. Or it's possible if we have a negative value for our step function that we could actually go below 0, so it would be the most negative number is also possible. Typically, though, in this course, we will see it be the most positive value. So the peak time is going to be pi divided by that damped frequency that we saw before. Then we have our maximum overshoot, the MP value. So here it can be a little bit tricky in the definition. It's the relative difference between the maximum value and the steady state value. So typically we're going to get some ratio. So we might get a value of, let's say, 0.6. Really what that 0.6 is telling us is that the maximum value is 60% greater than the value of the steady state. So the value we get out of MP is not the value of the response itself or the maximum value itself. It's basically how much greater than the steady state value is it. So if we multiply 100% by that value, that tells us the percent difference. And the settling time. There's a lot of different definitions or types of settling times we can use. Highlighted here is kind of the generic, if we want the X% settling time, how we could compute it. But here I have listed, just using that equation, more common settling times like the 1, the 2, and the 5% settling time. So the numerator, again, is just coming from taking the natural log of 1, 2, or 5, and that's how we're getting the value that we have there in the numerator. And then all the time, that's going to be divided by the damping ratio times the natural frequency. So what the settling time tells us is how long is it before the value of our function never exceeds X% plus or minus X% of the steady state value. So if we want to know the 5% settling time, that's how long it takes before the oscillations never go above 5% more than the steady state value, nor go below minus 5% of the steady state value.